Okay. Yeah. Hi, everyone. So, welcome again to the British Society for Geomorphology Postgraduate Forum. Geomorph Talks, Methods, Models, and More. This is our second webinar initiative of this year, and we have Dr. Alissa Flatley from UNSW, Australia. So, just give me a minute to introduce Dr. Flatley. She is geomorphologist, and she's working on terrestrial laser scanners and a lot of like geomorphic stuff, trying to map different things using various new techniques like uncrewed aerial vehicle, deriving lidars and stuff. So Dr. Flatley is presently a lecturer in physical geography at UNSW Canberra, and she completed her PhD in geomorphology in 2022 from University of Melbourne, where she worked on small arid zone streams in eastern Pilbara, Western Australia, and tried to learn about the implications of mining river relocation designs. Her recent research has used the TLS scanners to monitor various geomorphic environments from dunes, headwater rivers, and other protected landscapes. So, yeah, without any delay, I will ask Dr. Flatley to take over from here. Thank you.
Great. Thank you, Jayesh. Can I just check that you can still see my screen before I get going?
Yes, we
Great.
can see your
Okay.
screen. Yeah.
Thank you. So hello everyone. I'm really delighted to be here. I'm happy to take part in this webinar to provide some insights about key methodological approaches in geomorphology. My interest in terrestrial laser scanning kind of happened by accident. I was working in a department that was also in architecture, construction, and environment. So the construction staff had a wide variety of tools, and I thought, well, maybe I can apply these to geomorphology. And so over this webinar, I'm going to talk to you about some things that I've learnt, and it is very much a webinar about trial and error. So if you are thinking about using handheld terrestrial laser scanners for geomorphology, I hope that you enjoy the webinar and you're not too disappointed um, by the end of the session. So first of all, I would like to acknowledge the traditional custodians of the land where I am presenting. In Australia, it's common to give an acknowledgement to country. So I acknowledge the Ngunnawal people, who are the traditional owners of the Canberra region, and recognise their continuous connection to culture, community, and country. So for this webinar, I'm going to be giving a very brief introduction to scanning in geomorphology. I'm then going to talk about static terrestrial laser scanning. And at this point, I think it's really important to mention that a lot of the techniques that I'm talking about were pioneered quite a long time ago now. But really sort of there's been rapid advancements in the sort of the size of handheld terrestrial laser scanners. So we'll talk a bit about their static counterparts. I'll then talk about mobile mapping systems, and it's a bit of death by acronym in this webinar. I'll then talk about handheld TLS and introduce some of the TLS that I've been using for my research. And then I'll then talk through some key terminology around their operation. So we'll be talking about SLAM, loop closure, occlusion, IMU, GPS, and don't worry, you'll know what those mean by the end of the session. I'll then talk through a few survey suggestions, and I'll provide some examples. And I'll mention that some of these examples aren't pretty. It's kind of some point cloud nightmares, but I think it's important to showcase, I guess, failure as well as success. So scanning in geomorphology is not new. Obviously, the ability to rapidly acquire high-resolution topographic data has resulted in huge advances in landform mapping and landform monitoring. So I started my PhD looking at rivers, and some of the data sets that are available now were not available during my PhD, and these ones are phenomenal. So these are just two examples of some Victorian River lidar scans. These were conducted by airplane, but they give a really good example of the types of capabilities that we have in landform mapping. So I'm going to focus, I suppose, for this webinar on laser 3D scanners for surveying. And so I'm going to give a little quick overview of the technology. For those of you that aren't familiar with the scanning world, we typically can classify these into terrestrial 3D scanners. So these are things that are stationary, they are sort of mounted on a tripod, and the technology that they use is a laser point, a laser pulse. Some of their strengths are their long range detection and also their accuracy. And then on the other side, we have a whole variety of mobile mapping systems. So these are given the acronym MMS, and these are mobile. So these are scanners that can be mounted or handheld. And there's a wide variety. So when we're talking about MS, we're talking about scanners on trolleys, scanners on carts, handheld terrestrial laser scanners, yes, but also scanners mounted to backpacks, poles, drones, and things like this. So there are a wide variety. Of course, TLS stands for terrestrial laser scanner, and these were really pioneered in, I guess, the forestry space. So these are used quite frequently for mapping and monitoring of vegetation through time. We also use TLS in geomorphology, so these are used quite extensively to map different things like rockfalls, channel banks, also environments that are not particularly safe for field work to be undertaken, and so sort of the flanks of volcanoes, so on and so forth. And the main thing that these have in common is the way that they use lidar. So lidar stands for light detection and ranging. And it's really quietly become one of the most powerful tools in the modern world. So it's a remote sensing technology. It uses laser light to measure distances, detect objects, and create detailed 3D maps of environments. And these are often with centimeter level accuracy. When I started my PhD, I was using photogrammetry, so using a method called structure from motion. And so this operates under the same basic tenets as stereoscopic photogrammetry, in the sense that the 3D structure can be resolved from a series of overlapping offset images. So I said before that the advances in, I guess, mobile TLS technology, they do not take away from the fact that we still use static TLS, so tripod-based stationary TLS, for a lot of geomorphic mapping and a lot of monitoring and scientific research. And I wanted to highlight a few ways in which we still use static terrestrial laser scanners. So these have been used for studies of coastal change, classification and mapping of complex coastal environments like coastal cliff retreat, microtopography of salt marshes, and there's a reference list at the end if you're interested in looking at these in more detail. We also use them to monitor seagrass habitat, for dune ridges, dry bars in proglacial river systems. So there's really a wide variety of uses for these static TLS stationary settings. So there is something about teaching an old dog new tricks. And just because we have handheld TLS scanners now, I think I really want to reiterate that, just because we have handheld TLS, the stationary tripods are not dead in the ditch, and they still have a lot of capability in this field. I'm going to talk a little bit about benchmarking. So one of the concerns with geomorphic mapping is to ensure that we have a good understanding of how accurate they are in their mapping and surveying of reality. So the term, if you're not familiar with a benchmark, it's a term applied to any item used to mark a point as an elevation reference. It's also used as a term to kind of test the accuracy of a method against real world. So I wanted to highlight this particular benchmarking study that looked at terrestrial laser scanners, so static terrestrial laser scanners. And this study came out in 2019, and they, Emilia Guisado Pintado and her team, they looked at the 3D mapping efficiency of a drone versus terrestrial laser scanning over a beach dune. And they came to some good conclusions. They found that survey outcomes, so the sensor performance and survey success essentially was dependent on complexity of terrain undulations, terrain slope, vegetation, and point density. And they found that static terrestrial laser scanners perform better than UAV, so uncrewed aerial vehicle, over flat beaches than in vegetated dunes and vice versa. They also found that static TLS was found to be more effective on flatter, low-angled topography compared to areas with complex landforms or dense vegetation. Other studies as well show that soil type can also influence terrestrial laser scanner returns. So we'll just bear that in mind for the following slides. So how does this all fit together? Well, terrestrial scanners, the static ones are very useful, but there are some downfalls. So these surveys are associated with labor-intensive equipment setup. This can require multiple field days for surveys, which you typically would have overlapping scan data. And for that, terrestrial laser scanners have a much smaller aerial coverage compared to UAV-derived scans. To overcome some of these limitations on sort of scale and timing, a lot of terrestrial laser scanners have been mounted on varied mobile platforms, and these are otherwise described in the literature as mobile laser scanners, so MLS, or mobile mapping systems, MMS. So these have been deployed by mounting TLS onto carts, onto vehicles, snowmobiles, survey boats, and sledges. Here's a picture of a car-mounted MMS, and this was from a paper in 2008. So this is not new. Here is another example of a boat-based mobile laser scanner. So you can see they've got their mobility down, but it is still quite clunky to move about the scene. So then we have handheld TLS coming onto the scene. So my way of describing handheld TLS to I guess people outside of geomorphology or scanning is to liken it to a Star Trek tricorder. So quite Spock-like, you have your device and you walk around with it and you scan your environment. It also reminds me of kind of one of those memory wipers from Men in Black. So I'm going to talk through the typical structure of handheld TLS now, which are essentially a smaller version of the static counterpart. So this is a typical handheld terrestrial laser scanner, and I took this image from a recent paper that shows the structure of a TLS scanner that was developed. So this one, you can see the main lidar attachment is the DJI Livix Mid 360, so that's a 360 scanner. On the top of this one, there's a panoramic camera with fisheye lens. A handle which has the built-in battery within it. And then most TLS also have a base or a control point target, and this is to stabilize your TLS when you're starting to use it. So I'll talk about the camera aspect. It's not just to film your scan to show everyone how cool you are, how much you look like Spock. It's actually in part to colorize the point cloud. So the device there, the DJI Livix Mid 360, it will provide your point cloud, but it won't necessarily provide the color return for that scan. So these are often incorporated with a 360 camera, and the 360 camera will help colorize the point cloud. So it's an additional processing step after you've extracted your your point cloud from the TLS. So in terms of the device structure, handheld TLSs, they don't always have the camera as a separate attachment. Some are incorporated into one device, or again, developed as a series of connected parts. I'm going to talk through a few other examples of TLS that I've used. So this is the Leica BLK2Go. So this is a mobile scanner. So there have been rapid developments in handheld terrestrial laser scanners, resulting in their inclusion within other fields like architecture and construction. So a lot of the use cases and the research so far has been related to their accuracy and sort of rendering capability for internal structures. but I'm hoping to expand on that to think about benchmarking in geomorphic systems. So this one here is relatively light. It's 650 grams. And its pulse rate is 420,000 points per second. I promise I don't work for them. I just wanted to give you some indication of the type of capabilities. So this one has a range of 0.5 to 25 meters, which means you have to be within that range for the scanner to pick up the object that you are scanning. And it has a 10 millimeter accuracy for an internal setting. So the accuracy might get slightly lower when you're outside. And it has a 12 megapixel camera. The price point, if anyone's writing their letters to Santa, it is currently going for £27,000, which is, for what it does, it's very useful, but potentially not if you're just starting out doing research and you want to have a test case or a trial. Another example I'm going to talk about is the FJD Trion P1 lidar scanner. This one, like the one I showed you before, it has a secondary attachment. It's got the Insta360 on top of the LiDAR scanner, and that is for colorizing the point cloud. So you can use it without the camera. It just means that your point cloud will not be essentially colored in with the natural colors of the landscape. And these two things can basically change how you are viewing the point cloud. Essentially, something that is colorized is a lot easier to demonstrate to people, the landform that you've mapped. Whereas if you don't have the colors, you're maybe looking at the return for the GPS time or the point intensity, and it's not as intuitive to look at as a landscape. This one is a lot cheaper. So this one is about £7,000. So both of these values are in Great British pounds. So yeah, and I think it's fair to say you get what you pay for. And I think depending on what level of accuracy you need, I think there's definitely a case for both of these examples. So the one that I've been using most recently here in Australia is the FJD Trion. This one has a relative accuracy of up to 2 centimeters inside, so it's got a slightly lower accuracy than the Leica BLK2GO. It has a scanning range of 40 meters at 10% reflectivity. And I just want to talk through what that means. Hopefully the other terms here are fairly straightforward. So you can visualize your point cloud as you're scanning. So you're holding your scanner in your hand, and you might use something like a phone, and you'll have an app on your phone, and you can see the point cloud being I guess created as you're walking along. So that's quite a nice feature if you want to check that the scanner is picking up your points as you go. It's got a sort of a 360 lidar field of view. Some of them don't have a 360 field of view, so you have to sort of move them around a bit more, like your Jean-Luc Picard scanning a space planet. This one is also quite lightweight and portable. It's one kilogram, and this has a slightly lower points per second rate, so it's 200,000, so about half that of the Leica BLK2GO. So I was talking about this idea of scanning range. So this says it's got a scanning range of 40 meters at 10% reflectivity. And what that means is essentially that every object that is being scanned has a reflectivity about it. So highly reflective objects such as stainless steel or polished surfaces are going to be a challenge when you're completing a 3D laser survey. So if you're not familiar, this is a little diagram showing you principles of laser scanner data acquisition, and you can see the I guess the pulse, and you've got the first return pulse, the last return pulse. And in this example, it's showing you that water can reduce the reflectivity depending on the wavelength. So highly reflective objects, as I said, are challenging because they essentially create more noise in your point cloud. So this diagram down here is showing you two types of reflection. You can have diffused reflection. So this is where you've got a bumpy surface and there's a bit more scatter in the in the laser. And then you can have specular reflection. So specular reflection is one that is more representative of a sort of a shiny object, whereas diffused reflection is going to happen where you've got a surface that is associated with a rough kind of texture. And so I think it's quite important to be aware of how reflectivity of your particular scanning location can ultimately hinder, I guess, the accuracy of the device. But it's not all doom and gloom. I want to talk about why you would go handheld. So despite, I guess, despite the ease of like the increase in drones and in UAVs, there is an increasing cost associated with the training of drone pilots. There's ongoing costs for parts, insurance. There's more stringent legislation around UAV use. So despite their high initial costs, sort of mobile TLS survey methods can offer a flexible survey approach with low training that can be deployed quickly. So if you're writing a grant to get one as we speak, they are lightweight, readily deployable, no drone license is required. Minimal training, obviously there is some training in its use, but this is quite useful for field surveys and survey assistance, so the level of training required is obviously a lot lower. It is also useful in areas that you cannot fly in, and you can walk in and out with it, so it does make for a slightly simpler operation. I'm going to talk about I guess a simple workflow for this operation. This is a methods webinar, and this is kind of a simple workflow first. So here's a picture of a point cloud. So first of all, you would set up your project and connect your devices. Second of all, you would walk around and capture points, and hopefully this works. I'm going to press play. And so you walk around, and the color you can see is essentially a sped up version of the points being collected. I'm walking in a loop in this example. So this is a video of a rock platform, and the scan points are coded to GPS time. So I can play that again, and it just shows essentially me walking in an oval shape on a rock platform, and you can see sort of the points being collected as I walk. The next stage would be to end the project. So you cease scanning, you would download the data and then enjoy. So that's quite simple. However, what I found in reality is that you can set up your project, you can connect devices with each other. There's sometimes issues with Bluetooth connection if you've got a slightly older mobile device, so it might take 1 or 2 turns to get that seamless Bluetooth connection. You might then want to set up ground control points if you're doing a project that is going to require some sort of quality control. So then you would walk around and capture the points. You tend to split your survey after 20 minutes, and that's just for the device that I'm using at the moment. It just suggests starting a new scan every 20 minutes. You would then measure ground control point tiles. You would employ something called loop closure, which is something we're going to talk about later. It's just walking in a circular fashion to kind of close your loop. So your starting and finishing point would be at the same location. You would then end your project, collect your ground control point tiles, and then download data, colorize if this additional step is required as a secondary process. You would then work on cleaning your point cloud if you've had any mobile or very dynamic things happening in your scene, and then the standard quality assurance, quality control that would happen for any other surveys that you would use lidar or structure from motion for, and then enjoy. Yeah. So I want to talk now a little bit about some other terms that are connected to handheld terrestrial laser scanners. Hopefully this is not too boring. I think it's quite useful to know some of the terminology. So the first one I want to talk about is IMU, which stands for Inertial Measurement Units. And this is essentially used to guide the handheld laser scanner to let it know where it is in space. So almost all lidar data are going to be georeferenced. And georeferencing, if you're not familiar, is the process of aligning a digital image or data layer with real-world geographic coordinates, effectively giving it a specific location on the Earth's surface. So in this example here, we've got airborne laser scanners, MLS, which is mobile laser scanners, and TLS, terrestrial laser scanners. And the MLS and the ALS will typically have something called a GPS IMU, which is this inertial measurement unit. And this is pretty critical for the georeferencing aspect. And so this diagram is showing you a typical workflow for a change detection in a riverine environment. So you would take your scans, you would georeference to make sure that you've got an accurate scan. You would develop your point clouds, you might do some point coloring, you would, potentially filter, do some classification and so on. Your end outcome from this would be a digital surface model or a digital terrain model of either the vegetation being the surface or the ground being the terrain model. And then you can use these to look at your sort of change in your environment over time. But it's all fairly critical that you have an IMU GPS. So this is this inertial measurement unit. This is what they look like. So it kind of looks like an old-fashioned clock. But what they do, they're pretty integral to GPS systems. So they provide accurate navigation even when GPS signals are unavailable. They work by detecting linear acceleration and angular rate, which are then processed to determine the object's position and heading. So this data is crucial for applications such as dead reckoning. So this is when the system tracks the object's last position based on its last known location and motion data. IMUs are also used in conjunction with GPS to enhance navigation accuracy, especially in challenging environments where GPS signals might be weak or obstructed. And I will say, I'm not really an expert on IMU, but I know that they are very critical, and I've seen what happens to point clouds when they are not working well. The second terminology I want to introduce you to is this terminology called occlusions. So an occlusion refers to when, in this particular example for forestry, where you have stems, branches, twigs, or leaves that may not be scanned by static TLS as they're hidden by elements closer to the scanner. So occlusion is a significant challenge that can lead, particularly for the study of vegetation, that can lead to data gaps or incomplete representation of forest structures. It is caused by objects essentially blocking the laser pulses during scanning, which can occur in various forms like branches, poles, people, or other obstructions. And this can result in a lack of information about the structural complexity of that particular scene. And to mitigate against occlusions, researchers have developed different strategies, such as adjusting the scanning parameters, so changing the scanning angle or increasing the voxel size. For those of you that don't know, a voxel is a three-dimensional equivalent of a pixel. So these methods can aim to improve the accuracy or completeness of the data collected during laser scanning. So this particular example is showing you lower values for tree height due to occlusion. It's showing you at stand level, there's significant structural information was lost in the canopy range. And larger voxel sizes, so kind of 3D pixel sizes, reduced the relative information loss. Now, handheld mobile laser scanning has been used a lot more readily for forestry than it has geomorphology. So the equivalent of a handheld terrestrial laser scanner was first used in around 2012, using the movement of an operator as a platform. So really the first handheld TLS. And this example is showing the differences in the scan density and quality from TLS, so the static version, and the handheld mobile laser scanning. Now, this is from the same paper. This is showing you, I suppose, the location of the fixed TLS setup and also the walking pattern from the terrestrial laser scanner. So this one started in red and ended in dark blue. There's also been other work to prevent occlusion in forestry by scanning at different levels, so scanning at different elevations. So this diagram is showing you individual tree silhouettes that were derived from a full scan in winter, so number one, a full scan in summer, number two, ground scan in winter, and a ground scan in summer. And the idea behind this is that the walking paths for two trees were essentially the same under a ground scan and a full scan. However, in the full scan, they then took their handheld TLS and raised it above a platform to get a fuller kind of coverage to mitigate against occlusions. I will say occlusions are still a problem for geomorphology, and I think it's something that is going to be readily informed by, I guess, forestry research, I suppose. The next thing I wanted to talk about is an acronym called SLAM. So occlusions for forestry are and vegetation and anything that requires a very I guess high level of detail in the scan. Occlusions is something that you need to be aware of in your survey approach. The next thing is then SLAM. So SLAM is a broad term for a technological process developed in the 1980s. And it's referred to really as a chicken and an egg, I would say issue, opportunity. It stands for simultaneous localization and mapping. So this is essentially where we have robots navigating autonomously through new environments without a map. So this technology has paved the way for some mobile mapping. Yeah, and it's very useful, but ultimately you have to do both things at the same time. So autonomous navigation requires locating the machine in an environment while simultaneously generating a map of that environment. It's quite difficult to accomplish because the machine needs to have a map of its environment, but to estimate its location. But to generate a map, it needs to know its own location. So this is why it's sort of a never-ending circle of dependency. So it's known as the chicken and egg problem. So development of SLAM technology has contributed to solving this problem, and this can enhance the accuracy and the efficiency of mobile mapping. To give you probably a more relatable example, we use SLAM technology for self-cleaning robots. So this is an example of a roomer. And in the first diagram, you can see I guess the robot vacuum cleaning a room randomly without SLAM. And in the second diagram, you can see the robot is cleaning the room whilst understanding the room's layout. And there's a little diagram in the top right corner where it's understanding the changing conditions of the room. So in this diagram, a dog has left a mess and the robot has decided to avoid the mess and turn around. So this is kind of a good description of what SLAM is. And in terms of workflow for this, there are sensor-dependent processing and sensor-independent processing. And there's lots of things that are occurring on the front end. So this can be things like feature extraction, data association, feature tracking, and this idea of loop closure. Now, loop closure is particularly important for geomorphological scanning. It can be a lot more tricky to walk in a loop outside than it is inside. You know, inside we're confined by the walls of a building, and so we know, well, we've got to go up here, turn left, turn left, turn left, and we're back. However, loop closure in a natural environment can be a bit more challenging. So the idea of incorporating a round trip approach is essentially to avoid drift error propagation. So this term, loop closure, has been recognized as a method to produce superior point clouds that essentially align better to ground controlled point clouds. Yes, so loop closure is essentially walking from the start of your survey in a loop and just finishing your survey in the same point that you started. Sometimes when you have a handheld TLS and it's recognizing that you're veering away from your loop, it will sort of encourage you to walk back to where you started your survey. I'm going to move on to some examples now of where handheld TLS has been used in geomorphic applications. So the first example I'm going to use isn't from my own research, but I particularly like it as a case study. So this is a TLS, a handheld TLS being used in a narrow passage in a cave. So this is Re Tiberio's cave in Italy. And this research by Seville Aguareles et al., they actually used a static TLS, and they used the static TLS at the entrance to a cave. They then used a BLK 360, which is the image that you can see B on that figure. And then to get into some of those even smaller spots, they used the same BLK to go, which is the handheld TLS that I mentioned earlier. So they did this essentially to create a detailed map of the tunnels. There were some sections of the cave that had complicated passages due to the presence of boulders and reduced widths, and then the BLK to go, the handheld laser scanner, was used in this instance. One of the outcomes from this was a really detailed 3D map of a cave system. And they then used this information to highlight, I guess, some of the environmental history and the flooding behaviors for that particular environment. So I guess the benefits of using the handheld TLS in this study were that they could move a lot faster in extremely narrow, confined passages. So if you're claustrophobic, maybe not for you, but it is a really good example of how it's been integrated with IMU and 3 cameras to develop, I guess, a colorized point cloud of a cave passage. The next one I'm going to talk about is a little bit closer to home. At least I was in Swansea before I moved to Australia. And I mentioned earlier that I started to use handheld TLS because I was essentially in a department with architecture and construction, and I wanted to use some of these tools outside. So this is just part of a project that was looking at, I guess, the impacts of a pier wall construction on a small urban dune. So this was a small urban stabilized dune in Swansea Bay, just near the River Towie, so in this really the center of Swansea. And this was a really small 0.03 kilometer squared area in extent with a variety of terrain types, including vegetated dunes, sparsely vegetated foredune, bare sand, boardwalks, and high and low slope environments. And so this was my first foray, I guess, into terrestrial laser scanning with a handheld device. If you're not familiar with the location, these are some historic photos of Swansea. And so the first photo, figure A, is showing you Swansea Dune at the River Towie mouth, and this was taken in 1921. And if you look just by the letter A, that is the area that is of interest. So essentially this area, this pier wall was built, and it acts as an artificial headland, and it encourages sediment deposition and urban dune growth. So you can see this dune developing since the 20s. And so B shows you the same area, but in 1949. And then more recently, you can see a photo from 2024. So for context, this big grey barrier is one of those pointy fences, this sort of the 6 feet pointy fences, and you can see a lot of sediment being trapped in this system. As part of this project, there were some local works being done to effectively try to trap more sand in the dune system to avoid it overtopping the wall and causing potential hazardous issues. I think in 2018, I might be wrong with there were a series of wall repairs, and there was some slight damage damage caused to the dunes. And so you can see that damage indicated by picture D there. Now, typically you would, in this environment, you could just, you know, scan the site with a lidar drone or do some structure from motion. But this particular area had some survey challenges. So these included the site of interest was near a prison, and there was a new restriction that meant that there was a 400-meter no-fly zone around the prison. Essentially, offenders that break the rules have up to 10 years behind bars. And this is essentially to, and I'm sort of quoting from the government website here, but it was to create new security measures to cut the supply route of illegal drugs and phones. So naturally, the sort of appetite for doing drone surveys in this location was not very high. Typically, as well, there was poor weather conditions during scheduled surveys. We had a couple of surveys that we had to do a rain check on, and seagulls were quite a concern. Some of them were quite aggressive, I guess, during the mating season and the sort of chick raising season. So we were looking for alternative ways to conduct a survey. Now, I did mention that this survey does not look pretty. This one you can see for this example, I didn't do a full loop closure, but I wanted to show you what this survey looks like. So this is just a short video, and I think you see me zooming in, and you can see some people on the beach. If you zoom in closer, you can see some large woody debris on the foredune, or some wood there. And if you zoom in closer, you can even see the individual footprints in the sand. So this was from a terrestrial laser scan. And at the time, I was quite obsessed with the foredune, so I spent a lot of time scanning that area. And you can see from, I guess, from the video, you can see the individual footprints in this location. We chose this location for a case study really because it was a boardwalk dune, so there was already a boardwalk in place, so I felt that it would not disturb the dune in more detail. So to undertake this survey, I planned the survey in advance and did a series of loops around existing boardwalks. And you can see loop 1 is the part of the dune that was previously damaged. There were some issues, I suppose, with the scan. So this is a cloud point. This is a point cloud in your nightmares. So you've completed the survey, and it looks good until you zoom in and you start to see, sorry for the flickering, you start to see some weird things happening, like cars being parked too close together in an unnatural state, some building misalignment, which essentially means that there's a lot more noise in the point cloud compared to what you would want from a cleaner point cloud. At that point, I found it quite hard to trust the rest of the point cloud, given that there were some interpolation issues. I don't think so that's the kind of the main giveaway. It's always helpful if you can use a building to just check I guess the cleanliness of your point cloud, and you can see a lot of overlapping cars as well that would need to be manually cleaned. Another example I want to talk about, and I'm just conscious of time, so I think this might be one of the last ones. An example now coming back to Australia. So this is Benjello Beach in New South Wales. Similarly, a dune environment, just a slightly different climate. This location is on the east coast of Australia. It's just south of Bateman's Bay, which is south of Sydney. And this location has been part of a long-term research project since the 1970s. So there have been monthly to bi-monthly surveys since 1972. And in this particular environment, there have been some intense storm events, which have been driven by tropical and extratropical storms. These have caused wave overtopping and removal of foredune, creating a scarp of 1 to 2 meters. So this makes it quite vulnerable to future wave impacts. This particular map was produced by my colleague Tom Oliver and his team, but we essentially wanted to try to implement TLS to get a fuller picture of that, I guess, scarp on the dune. So a beach scan was conducted across the dune between two of these long-term beach survey transects. I think it was P3 and P2. Now, this next example also doesn't look very pretty, but this is an example of a non-colorized point cloud. Hopefully that makes sense. You can see here, so the return is not based on the color of that particular environment. It's just based on, I think this is GPS time or intensity. What I wanted to show you here is it's just a screenshot from Cloud Compare. So Cloud Compare, if you're not familiar, is an open source point cloud, I guess, processing tool, which you can clean your point clouds, you can make your digital surface models, you can do some interpolation and it's, you can do a lot with it. Basically, you could have a whole session on this particular software, but in this one, this point cloud was just imported into Cloud Compare, and then I rasterized it to turn it into a DEM. Another example I wanted to give you is just a rock platform. So this workflow is just talking about how you would integrate your camera and then colorize your point cloud. So the 360 camera in the FJD Tryon essentially scans the scene to provide you with the color for your particular point cloud. So this is obviously a fishbowl picture of the rock platform, and this rock platform is just to the north of this other location. Again, I think we saw this video earlier, but this is just me learning to use the TLS and walking in an oval shape, just collecting those points as we go. And then the final output was a digital surface model. Again, it doesn't look too impressive when it's on a tiny screen, you know, on Teams, but once you zoom in, you can see individual boulders and sort of the cracks in the rock platform. So this is quite useful in our case for a teaching perspective. And if you want to see what that looks like, just in its point cloud, this is showing you the same point cloud, but this is showing you, I guess, the intensity. So the scalar field is showing you the intensity, and you can see some, I think, some human noise there. This particular location was of interest for overhanging vegetation on a curved bank. So this is showing you, I guess, the real world location of what we were trying to scan. So that's the point cloud. And the patch that you see in green is essentially this overhanging vegetation, this very, kind of undulating terrain with different types of vegetation being captured. And this is the same sort of bank, and there is some erosion in that location, which I think was fairly well captured. This is the same point cloud, but I just wanted to show what that video looks like. So this at the moment has not been colorized. It's very much a work in progress. But I just wanted to show you, I guess, how that looks. In terms of how long this scan took, I think it was a 6-minute scan, so a very short walk. So I think handheld TLS, I think it really much depends on the size and the scale of your interests, but you can see me just rotating the point cloud there, and it does a pretty good job of capturing that curved bank. So I think that's almost it. Thank you for bearing with me. I have a few suggestions and a few final kind of anecdotes. This is very much a work in progress. And so I'm hoping to publish a paper on some of the kind of benchmarking work that we've been doing so far. So if you are interested in it, feel free to add me on LinkedIn or send me an email, and I can keep in touch with you. For all handheld terrestrial laser scanners, if you can, try before you buy. Obviously, that's not an option for everyone, but you can now rent handheld terrestrial laser scanners, and I do think it is worth the 200 or 300 pounds before you invest in a more long-term, I guess, purchase. Plan your surveys ahead of time. I've shown you some examples of just ad hoc scans. For loop closure in natural environments, I know is not always practical. So it really depends on where you are. You know, if you're crossing a river, you have to be careful. You have to plan your surveys ahead of time. The locations that I was scanning, the site in Swansea was kind of perfect because it had a boardwalk, and so there was no extra trampling. And this is somewhat tongue-in-cheek, but explore capabilities of architecture, environment, and construction departments if you have them on your campus. Sometimes they'll have terrestrial laser scanners that have been kept inside their whole life, and they're just itching to get outside. Lastly, think about what resolution is required for your particular project. So there are obviously big differences between centimeter and millimeter level accuracy. And as we've seen from these two case studies, there's a big difference in the cost of devices. So if you don't need millimeter accuracy, maybe don't try to get millimeter level accuracy. Thank you so much for listening, and I appreciate you putting up with me. It's now nearly midnight here, but I'm happy to answer any questions if you have them. I'll just have a quick shout out. This ongoing work has been supported by a great team, including some researchers at University of Wales Trinity St David and the team here at University of New South Wales. Okay. Thank you.
Yeah, thanks, Alissa, for that wonderful
Thanks.
presentation. Yeah, it's excellent to see your results, and also I pretty much like the way you have taken the presentation, going into every details, how the principles that walk behind. We are always interested in applications, but we sometimes forget like how the machine works. So thank you for taking
Yep.
through that. So
I
yes,
hope it met
anyone
the
if
brief. Yep.
yeah, but yeah, thank you for taking through that. So yeah, if anyone has any questions, feel free to unmute yourself and ask.
Hello, Edward.
Hello, Edward. Yeah, you can go ahead.
Hello. So there's certain mobile devices that have lidar scanners built into them at
Yes.
relatively low cost. Do you have an opinion on those and how they compare to what you're presenting here?
Yeah, I haven't had a chance to use them because my phone is quite old-fashioned, so it doesn't have the LiDAR capability. But I think it would probably be really good for kind of outcrops or you know, small locations. I did have a colleague do some rock art scanning in the Flinders Ranges in Australia, and they showed me some of the output from their LiDAR scans, and they were quite impressive, but I haven't had a go at them myself. It would be a good follow-up webinar.
Thanks so much.
Yep. Thanks, Edward.
Yeah, thanks, Edward. So yeah, there is a couple of questions in the chat. So Dr. Priyank Patel asks a query about mobile laser scanners at two ends of the spectrum. How does Faro Orbis compare to Lysia BLK360? And despite its limited range, how precise is the iPad lidar scanner for mapping geomorphological features?
Thank you. I will be honest, I haven't used some of these devices, so I would just be guessing. Yeah, if anyone else is listening to the YouTube and you've used these, feel free to let me know. I think my general feeling is that the so I can't speak to the Leica BLK360 because that's the static TLS, and I haven't had much experience with that one either. But the Leica BLK2GO was really intuitive to use, and it had a really high point density. But I did find in my particular location there were some sort of georeferencing errors. But I'm 50% sure that's human error rather than sort of technological error. As for the iPad LiDAR question, that's similar to Edwards, and I haven't had much experience with that, but I'd be keen to try that out as well.
Yeah, thanks.
Yeah.
Yeah, there are a couple of papers I've seen, maybe in scientific reports, some maybe in geomorphology, where people have used the iPad lidar scanner to scan some features. So it would be very interesting to look and explore them more vividly, I guess.
Yeah.
Dan Goss has one question to ask you. So thank you. He says, out of interest, how do you normally georeference SLAM MLS datasets? I currently just manually align with TLS. What targets do you normally use?
Yeah, that's a really good question. So at the moment, I've been sort of doing some alignment with some ground control points and some benchmarks. For targets, it just so happens that I've got a few, and I wasn't planning this. I'm actually just using these stickers. So these are just the little targets. They're similar to the larger targets that you would stake down. These targets just came with the handheld TLS that I purchased, but I do have plans to, I guess, mount them onto a board that I can then peg into the ground so that they don't fly away. I hope that answers your question, but if not, feel free to email me.
I think if anyone else have any questions, any quick question, or so Dan says thanks. If there's not, so I would like to thank you very much. I would not take much of your time because it's already midnight over there. Thank you, Alissa, for this talk, and thank you for just agreeing to this webinar. This webinar should be on YouTube soon, and and we would love to have a follow-up sometime next year if you have more results, and we can have a follow-up webinar on this.
Fingers crossed.
Fingers crossed. And for participants and for you as well, there would be another webinar in December, of 18th December. So the timing is 3 to 4 p.m. UK time. So I think it wouldn't be possible for Alissa. But if you guys are interested in microplastic sedimentology, so Dr. Catherine Russell from Loughborough has agreed for the webinar. So just watch out our space in LinkedIn, in Blue Sky and Instagram, where we would be posting that soon. Thank you everyone. And is there anything? Oh, okay. So thank you everyone, and have a nice day and good night to you.
Thank you. Good night, everyone.
Thank you.
Thanks.
Thank you.